This is Sleepy Scientist, where science flows slowly. Tonight's story is about something ordinary, used every day, slippery, bubbly, forgotten the moment it washes down the drain. This is the science of soap. Soap is not just a liquid. It is not just a bar. It is not just something that smells like lemons or flowers or mint. Soap is a chemical, a very old one, a clever one. It works not by killing dirt, but by surrounding it and lifting it away. Soap is made from fat and alkali. Fat can come from animals or plants. Alkali is often sodium hydroxide, also called lye. When the two are combined in the right proportions, they react. This reaction is called saponification. It is not fast. It is not violent. It is patient chemistry. Fat molecules are made of triglycerides. Each triglyceride contains a glycerol head and 3 fatty acid tails. When mixed with alkali, the tails break off. They bond with the sodium. The result is soap. Soap molecules have 2 distinct parts. One end is hydrophilic. It loves water. The other end is hydrophobic. It fears water, but loves oil and grease. This two-sided nature is the key. It is what makes soap work. When soap is added to water, the molecules float around freely. When they encounter oil or dirt, the hydrophobic ends dig in. They burrow into the grime. The hydrophilic ends remain outside, touching the water. Soap molecules begin to form tiny bubbles around the dirt. These bubbles are called micelles. A micelle is like a tiny cage. Soap surrounds the oil, traps it, and lifts it away. The water carries it all down the drain. Dirt, oil, germs, all gone because of the structure of soap. Soap does not need to be antibacterial to remove bacteria. The physical act of surrounding and rinsing is enough. But some soaps do contain additional agents. Chemicals like triclosan. These can kill bacteria more directly, but overuse may lead to resistance. Plain soap often works just as well. The earliest soaps were made over 4,000 years ago. Clay tablets from ancient Babylon mention boiling fats with ash. Ash contains potassium carbonate, a natural alkali. Mixed with water, it becomes a cleaning solution. Egyptians used similar mixtures. So did the Romans. Soap was not always used for hygiene. It was often for washing clothes or preparing wool. The idea of bathing with soap spread slowly. In medieval Europe, soap making became a trade. In Aleppo, Syria, soaps were made with olive oil and laurel oil and cured for months. Castile soap from Spain used only olive oil. It became prized for its gentleness. Over time, different oils were added: coconut, palm, animal fats. Each one gave different properties: lather, hardness, moisture. Today, soaps are mass-produced, but the chemistry is the same. Fat, alkali, water, react, cure, clean. Soap and detergent are not the same. Soap is made from natural fats. Detergents are synthetic. Soap reacts with minerals in hard water, forming soap scum. Detergents do not. Detergents also work in cold water. Soap may need heat. In laundry, dishes, and shampoos, detergents are often preferred. In hand washing, soap remains the classic choice. Foam is not what makes soap clean. Bubbles are a side effect, not a cause. People associate foam with effectiveness. So many products are designed to foam more. But foam is air. It does not lift oil. It does not kill germs. It just looks clean. Real cleaning happens at the molecular level. In silence, invisible, chemical. Soap also breaks down viruses. Viruses like the flu or coronavirus are wrapped in a lipid envelope. This envelope is a fatty layer. Soap's hydrophobic end inserts into the envelope. It pulls it apart. The virus is destroyed. Not by poison, but by dismantling its skin. This is why hand washing works, and why 20 seconds matter. More time, more soap, more micelles, more destruction. Water alone cannot clean oil. Oil and water do not mix. Soap is the bridge. One side bonds to grease, the other to water. It joins opposites and removes them both. Without soap, oil sticks. It clings to skin, to clothes, to plates. With soap, it lets go. The pH of soap is typically 9 to 10. Mildly basic. This helps break down fatty acids, but it can dry skin. That is why some soaps add moisturizers. Glycerin is often included. It draws moisture in and softens. Other soaps add fragrance, or color, or antibacterial agents. These are extras. The core remains the same. Soap is not complex, but it is precise. In a microscope, soap films shimmer, thin layers, iridescent swirls. These are not random. They are caused by interference, light waves reflecting off both surfaces of the film. Different thicknesses produce different colors. It is physics, not magic. And yet, it looks magical. Some scientists study soap films to understand fluid dynamics. Others study micelles to design drug delivery systems. Some use soap bubbles to explain geometry and pressure. Soap is a tool, a lens, a bridge between disciplines. Soap can be solid, liquid, or foam. It can come in flakes, bars, gels, or powders. Its form does not change its function. Always, it seeks dirt, surrounds it, lifts it, and flows away. In chemistry, soap belongs to a group called surfactants, surface active agents. They reduce surface tension. This allows water to spread and penetrate more easily. Without surfactants, water beads up. With them, it flows. It enters crevices. It loosens particles. Soap is one kind of surfactant. Others are used in everything from toothpaste to paint. In nature, some animals produce soap-like substances. Certain frogs secrete foam nests. Some fish produce mucus that behaves like a surfactant. Even certain plants contain saponins, natural soaps. The world has always known how to clean, long before humans named the process. Soap does not stay clean. It dissolves. It melts. It breaks apart. Used soap shrinks over time. A slow erosion, a gentle reminder that it gives itself away. Soap does not stain. It removes stains. It leaves no mark, only absence. It is a transient thing, made to disappear, and when it is gone, you are clean, or the plate is clean, or the shirt, or the floor, but the soap remains on the hands. The molecules linger until rinsed away. No ceremony, no sound, just chemistry and the whisper of water. This is what soap does. It does not fight. It does not burn. It surrounds, it carries, it leaves fat, alkali, micelle, drain, a process that began 4,000 years ago, still happening now, every moment, in kitchens, in bathrooms, in hospitals, in space, the same reaction, the same removal, the same result. Soap works because it knows how to let go, and because, quietly, it changes everything it touches. Soap works because it knows how to let go, and because, quietly, it changes everything it touches. It surrounds what does not belong, and lifts it away. But some things are not lifted. Some things are left behind. Too heavy, too stubborn, too ancient. Some things never leave. They collect, settle, remain. One of those things is sand. Sand is defined not by what it is, but by what it measures. A grain of sand ranges in size from 0.0625 to 2 millimeters. Smaller than that is called silt. Larger than that is called gravel. Sand is not a substance. It is a size, a category, a texture. It is what happens to rock when enough time passes. Most sand on Earth is made of quartz, a hard mineral composed of silicon dioxide. Quartz does not dissolve easily. It does not wear away quickly. It survives where other minerals crumble. Quartz is born inside larger rocks, igneous, metamorphic, sedimentary. As water flows, as wind scrapes, as ice grinds, the rocks fracture. Quartz breaks free. The pieces shrink, crack, tumble, round off, until all that is left is sand. Not all sand is quartz. Some sand is made of calcium carbonate. Tiny shells, coral fragments, and skeletal remains of marine organisms. Some sand is made of volcanic glass. Black, heavy, magnetic in places. Some sand is green, formed from a mineral called olivine. Some is red, or pink, or white. Color tells the story of origin. Composition tells the story of age. But size defines what we call sand. Desert sand and beach sand are not the same. Desert sand is smoother, wind-polished, uniform, too smooth, in fact, for making concrete. Construction requires angular grains, like those from rivers or crushed stone. This is why countries surrounded by desert still import sand for building. The world has plenty of sand, but not all of it is useful. Sand moves. It does not sit still, not forever. Wind lifts it, water pulls it, waves sort it, gravity brings it down again. Sand bounces across deserts in a motion called saltation, a pattern of tiny leaps and falls. Over time, this motion builds dunes, crescent-shaped hills, shifting, flowing, alive. Some dunes make noise, low, rumbling tones caused by the synchronized movement of grains. These are called singing dunes. Their voices are studied, but not fully understood. In rivers, sand is carried by suspension. In oceans, it is sorted by tide and wave. On beaches, it piles and flattens, rises and recedes, builds and vanishes. Beaches are not permanent. They are temporary balances, edges of land in constant negotiation with the sea. A handful of sand contains hundreds of thousands of grains. A beach contains more than can be counted. The Sahara contains more than any one person could comprehend. But sand is not infinite. The global demand for sand, for concrete, for glass, for electronics, continues to grow. Mining disrupts rivers, destroys coastlines, changes ecosystems. In some places, sand mafias operate illegally, removing sand by night, guarding it with weapons, killing to control it. This is not the future. It is happening now. The Sahara Desert, the largest hot desert on Earth, is not ancient. 5,000 years ago, it was green. Lakes, trees, animals. Then climate shifted. The rain stopped. The sand spread. Deserts are not just places. They are processes. Sand is used in more than construction. It becomes glass when heated to high temperatures, over 1,700 degrees Celsius. Additives control its color, clarity, and strength. Glass is made, but sand is what allows it to exist. In electronics, high-purity quartz sand is refined into silicon. This silicon becomes microchips, transistors, processors. Sand becomes thought, calculation, memory. The device reading this sentence likely contains sand. Refined, printed, activated. In nature, sand preserves. Sandstone can trap fossils. Layer upon layer of sediment presses down. Air is excluded. Bones turn to stone. The past waits inside rock because sand was present. Under a microscope, sand grains are not smooth. They are jagged, cracked, unique. Each one has its own geometry, its own history, its own path, from stone to grain. Some are pitted by salt, some scratched by ice, some etched by wind. No two are exactly alike. On the moon, sand is called regolith. It is not formed by water or wind. It is formed by impact. Micrometeorites shatter lunar rock into fine powder. The grains are sharper than Earth sand. They cling to fabric. They pierce boots. They are alien, but still, they are sand. In science, sand is used to study flow. Granular physics is its own branch of study. Sand behaves like a solid and like a liquid, but is neither. When poured, it flows. When packed, it resists. It can collapse suddenly. It can trick machines. Engineers study it. Physicists model it. Still, it resists easy explanation. In language, sand is metaphor. Time is measured in hourglasses. Empires are said to be built on sand, unstable, temporary. To be lost in the sand is to be forgotten. To bury your head in the sand is to avoid truth. Sand surrounds stories and becomes one itself. Sand is slow. It accumulates. It stays. It does not burn like fire. It does not drift like air. It does not dissolve like sugar. It is what is left after everything else has broken down, a remainder. To clean a surface, soap surrounds particles and removes them. To shape a coastline, sand collects and shifts. To build, sand is molded. To erase, sand is used to smooth. It is passive, but powerful. The next time a beach is walked, or a shoe is emptied, or a city is paved, there is sand, invisible in purpose, unseen in process, but always present. What exactly is sand? It is what remains. Sand is what remains. After time, after pressure, after erosion, it collects in deserts. It drifts along beaches. It waits under oceans, and it waits under the moon. The moon's surface is also covered in fine particles. It is not sand in the earthly sense, but it behaves in familiar ways. Broken rock, sharp dust, created not by water, but by impact. Yet, the moon does more than reflect light. It shapes Earth itself, quietly, constantly, and always from afar. The moon affects Earth in many ways. Its influence is gravitational. It is visible in oceans. It is felt in time and measured in motion. Without the moon, Earth would not be the same. The most visible effect is the tide. Earth's oceans rise and fall, not randomly, not by wind alone, but by the pull of the moon. As the moon orbits Earth, its gravity pulls on water. The side of Earth facing the moon bulges slightly. So does the side opposite. This creates two high tides, one where the moon pulls, one on the far side. Between these bulges are low tides. As Earth rotates, different areas move through these tidal zones. The result is a cycle: two high tides, two low tides, roughly every 24 hours. The sun also affects tides, but the moon's effect is stronger because it is closer. When the sun and moon align during a new moon or full moon, their forces combine. This causes spring tides, the highest and lowest tides. When the sun and moon form a right angle during first and third quarters, their forces partially cancel. This causes neap tides, smaller tidal shifts. These cycles repeat every month, every ocean, every shore. Tides do more than move water. They shape coasts, carve cliffs, feed estuaries. They also stir nutrients. Tides oxygenate shallow seas. They influence fish behavior. They even affect coral spawning. Without tides, marine life would be different. Without the moon, tides would be weaker, much weaker, just 1/3 of their current strength. The moon also affects Earth's rotation. Long ago, Earth spun faster. A day was just 6 hours long. The moon has been slowly pulling on Earth's spin, creating a braking effect known as tidal friction. This process lengthens the day by about 1.7 milliseconds per century. It is slow, but measurable. As the moon pulls on Earth, Earth pulls on the moon. This exchange causes the moon to move away. Each year, it recedes by 3.8 centimeters, a finger's width, a quiet drift. This has been measured with lasers reflected off mirrors left by Apollo missions. The moon is leaving, very slowly, in hundreds of millions of years. It will be farther, smaller in the sky, its tides weaker, its eclipses partial. The moon also stabilizes Earth's tilt. Earth rotates on a tilted axis, about 23.5 degrees. This tilt creates seasons. Without it, there would be no summer or winter, just eternal equator heat and polar cold. The moon's gravity helps keep that tilt steady. It prevents wild wobbles. It keeps Earth's orientation stable. Without the moon, the tilt might swing from nearly zero to extreme angles. Over thousands of years, climates would shift. Glaciers would advance and retreat. Rain belts would move. Habitability would change. Life, if it existed at all, would be different. The moon affects light. It reflects sunlight softly. Its surface is bright gray, not glowing, but illuminated. Moonlight guides animals. Nocturnal creatures hunt or hide by its glow. Crabs time their mating. Birds migrate by moonlight. Coral release eggs during full moons. In darkness, the moon becomes a calendar. Even humans once used it to track time. A lunar month, from one new moon to the next, lasts about. Our word month comes from moon. The moon influences human sleep. Studies suggest sleep is lighter near full moons. Melatonin drops slightly. Deep sleep decreases. The reasons are unclear. Perhaps it's light. Perhaps it's evolutionary memory. Or perhaps it is simply rhythm. The moon has been above Earth for over 4 billion years. Its pull is older than language. Even without understanding, organisms respond. Culturally, the moon is a symbol. In stories, it is linked to change, to time, to emotion. In Hindu tradition, the moon is Chandra, a god of the mind. In Islamic calendars, months begin with the crescent moon. In Chinese tradition, the moon festival honors reunion. Poets compare the moon to longing, to distance, to silence. Its phases mirror moods. Scientifically, the moon is a natural satellite. It formed after a collision. A Mars-sized body struck early Earth. The debris collected and cooled and became the moon. This theory is called the giant impact hypothesis. It explains the moon's composition, its orbit, its relationship to Earth. The moon is part of Earth's history, torn from it and forever orbiting. The moon has no atmosphere, no weather, no flowing water, no sound, but its surface holds memory. Craters never erode, footprints remain. For centuries, dust remains where it falls. It is a mirror, not just of light, but of motion, gravity, and time. When the moon eclipses the sun, it fits perfectly. This is a coincidence of scale and distance. The sun is 400 times wider than the moon, but it is also 400 times farther away. So the two appear the same size. For now, in the distant future, as the moon drifts away, total solar eclipses will end. The sun will no longer be hidden completely, only partially. This moment, this alignment, is temporary. A cosmic coincidence. The moon also inspires silence. No sound crosses its surface. No wind shapes its dust. It rises and sets and rises again, not in noise, but in quiet rhythm. What does the moon do? It pulls, it reflects, it slows, it balances, it marks time, it stirs oceans, and it steadies worlds, all without touching. A companion to Earth from a distance.